Okay, so what is an intermediate value theorem? So let's suppose a function is continuous, right? So the function is continuous on an interval AB. Okay, let's say, okay, both parts inclusive. So let's say this is A, this is B. Okay, then naturally you can find two values, right? What's the value? You can find FA and FB, right? You have two values. And let's suppose, right, without losing generosity, I mean, without, being, so we can suppose FA is smaller than FB. Okay. Of course, it could be the case FA and FB are the same, or FA is larger than FB, but you'll see it doesn't really matter. Okay. Let's suppose FA is smaller than FB. So on a graph, it will look like this, right? You have, so here is the starting point of the function, right? Let's say FB is, the value is like this, right? So this will be the endpoint of the function. Okay. So now, because it's a continuous function, right? So I don't know what's the shape of the function, but what I know is when I connect these 2 points, no matter how I connect them, I will cover all the values between FA and FB. Okay, so no matter you draw a straight line or you draw any weird curve or whatever, you will see you will always cover all the values between FA and FB. Okay, let's say you draw the curve like this. Okay, you see, okay, FA, FB, they are covered in this part. You draw the curve even like this, you can see FA, all the values between FA and FB, they're covered somewhere in the function. Right? So that's what this theorem is talking about. Okay, why? Because fx is continuous. That's the most important thing. Because if fx is not continuous, for example, I can just draw, right? I can just draw this function. This is not a continuous function. And this function will not cover these values. Okay. For example, I draw this function. This is not a continuous function. So this continuous function will not cover these values. Okay. So that's why it must be, fx must be continuous on A and B. Okay, so what's the math language of this theorem? So, okay, so first fx must be continuous on AB. Then for any x, okay, let's say for any value, right, for any value y between FA and FB, right? You can find x between A and B. Okay, such that fx is equal to that y. Okay, let's call this y0, x0, right, to be, because usually x, y, they are like variables. So if x0, y0, they are like a fixed value. So what does that mean on the graph? So FA, FB, right? Let's find any value between FA and FB. For example, this point. Okay, then, for example, this value. Okay, then no matter how you draw this function, you can always find x, right? So let's say y0 is here, then you can always find an x between AB such that, fx is y, right? No matter how you draw this curve. Okay. For example, right, if you draw the curve, you anyhow draw the curve, right? You draw the curve like this. then for this y naught, you can find an x naught between a and b such that fx naught is y naught. Right? You can always find such a point. Maybe there are sometimes 2 points, right? If the function looks like this, you can find 2 points. It's also fine. But the thing is, you can at least find 1 point. Okay, it could be more than 1 point, but at least there's at least 1 point. Okay, so I hope this will give you some, intuition of what this theorem is talking about. Okay, then how do we apply it? For example, in problem 3, use the intermediate value theorem. So this theorem is called the intermediate value theorem. Okay, so in short, we just call it IVT. Okay, to show that there's a root of the equation 1 minus x cubed plus sine x in the interval in the interval 0, 1. Okay, it asks you to prove it asks you to prove this equation has at least a root right? It has at least one root in the interval 0, 1. Okay. So first, let's create a function, and the function is the left-hand side minus the right-hand side. Okay, let's create such a function. And because the interval we are talking about is from 0 to 1, right? So first thing, this is a continuous function, right? This function is continuous on the interval 0 to 1, okay? You don't have to prove this. Why? Because it's just a combination of the basic functions. Like sine x, it's continuous everywhere. Like a polynomial, it's continuous everywhere. So put them together, right? Addition, subtraction, it's still continuous. So you don't have to prove why it's continuous, but you need to state this, okay? Then it is continuous on 0, 1. Then the second step, you just have to figure out what is f0, right? Just sub in. It is just 1 cubed minus 0 is just 1. And f1, okay, is 1 minus 1 cubed minus sine 1. It's just negative sine 1. Okay, negative sine 1, use your calculator or not. It doesn't matter, but the thing is it's smaller than 0. Okay, here f1, it's greater than 0. Okay, so now, because 0 is a value, because 0 is between f0 and f1, okay, f0 is negative 1, it's a negative number. Sorry, f0 is 1, it's a positive number. f1 is negative sine 1, it's a negative number. So because 0 is between this positive number and negative number, then by the intermediate value theorem, by the IVT, there must be a, let's call it x naught. There must be an x naught between 0 and 1 such that fx0 is 0. Okay, so that's the intermediate value theorem. So for any value between the starting point and the end point, there must be an x value, okay, giving us fx is that value. So in this special case, that value is 0. Okay, so that's a proof. You can see there's a solution of fx is equal to 0. You know, fx is equal to 0. That solution will also be the solution of sine x is equal to 1 minus x cubed, right? It will be the same thing. So that will be the proof of question 3.